Okay, my talk today will be about an example by Bhatwadekar and Dutta. And first of all, I would like to apologize because of my English and because of it seems that this talk wouldn't be so interesting as I planned, because I have done some computations this January, and when I have done them, I thought that it's very interesting and everybody enjoy when I give a talk in this field. And when I prepare this talk, I understand that maybe not everybody will be enjoying this, but nevertheless, let us try.
Just a continuation of our discussion about preparing in advance.
Oh, okay. The problem is that. Okay. First of all, let us begin with some philosophical introduction. In our field of research, which is, I hope, somehow affine algebraic geometry, there are some beautiful, interesting, and complicated problems. And if we do some investigations in this field, we should think sometimes at least about these complicated problems. But good complicated problems organized as follows. There is just this problem, and there are some facts around in this field, and if somebody wants to solve this problem, of course it's a good opportunity if you can solve it just by one step, but you investigate something around, investigate some partial results and some cases of these problems, and then you have some experience, you can try to solve this problem. But in these beautiful, interesting problems of affine algebraic geometry, the situation is rather different, because you have not this area. For example, Jacobian conjecture. Okay, there is a beautiful conjecture. If somebody will solve this conjecture, it would be very nice. But what about particular cases? Case n equals to 1 is trivial. Case n equals to 2 is open. So you have not any field to have some experience, and if you try to investigate this problem, you should investigate it just by one step. Okay, and what to do with this situation? Maybe we will try to have partial results when we prove that for example, polynomials of some kind, some special forms, these problems are true. But I think that the most interesting partial results is some candidates for counterexamples. When you investigate these candidates for counterexamples, then if you prove that they are counterexamples, that would be the solution of this problem. And if you overcome some difficulties to prove that this is not a counterexample, you have some experience which can be applied to general case. Okay, nevertheless, my thought was that you should consider some known candidates for counterexamples to some problems. And okay, let us start with two problems. The first one is epimorphism problem. I should say that I based on survey due to Neena Gupta with this title. Okay, epimorphism problem. You have a field, let it be complex numbers. Of course, it can be any field which is algebraically closed and of zero characteristics, but I wouldn't like to consider positive characteristic because there are some very different effects in positive characteristics. You have just polynomial algebra. And you have a polynomial f in this algebra. And you know that the quotient algebra modular the ideal generated by this polynomial is the polynomial algebra. Let me denote it by this. So this is polynomials in n-1 variables over C. Is it true that f is a coordinate? F is coordinate means that this algebra, let it be B. Oh, I'm sorry. This algebra, let it be A. This algebra can be considered as an algebra of polynomials with one variable is f. These are some polynomials in x. F is n-1, yes. F is this f, and there are some other polynomials in n variables such that A is polynomial ring in f and y i's. Okay, this is epimorphism problem. And let me try to consider one more problem, which is called A2 fibration. For this problem, we should give some definitions. Firstly, let me remind the definition of a flat model. Let n be a model over a ring R. And let m prime is a submodel of M. These are also modulus over R. And you have injection of M prime to M. Then you consider tangent products of these models with N. And if this inclusion follows that M prime tensor N is included in M tensor N, then N is flat.
For any pair M prime and
For any epimorphism of models.
for any injection.
And the map should be the tensor product with the height.
Yes, of course. This is natural map which is and it should be mentioned that if tensor product with n maps epimorphism to epimorphism, then it maps exact sequences to exact sequences.
It's a
This
mono.
will not be a
Monomorphism to monomorphism, then it move exact sequences to exact sequences because tensor product is always
Right, exact.
right exact. Yes. Okay, let P be a prime ideal in R, and then we can consider localization of this ring in a prime. It's prime. In the
R
prime.
is a commutative ring.
R is a commutative ring, yes, of course.
No other condition.
Oh, no.
Without zero divisors.
Oh, no, just any commutative ring. But of course, we somehow would like to consider some affine rings finitely generated and without nilpotence. But now just any commutative ring with unit. Okay, we have prime divisor. You can consider localization. It is a local ring,
No,
and
it's not a local ring.
localization is a local ring.
In a prime divisor. In a business.
Yes, of course. You can divide on anything which is not in this divisor, and the divisor is unique maximum. And you consider the residual field, just modular this unique maximal divisor. This is a field which we denote K of P. And okay, let us say that let R be a subalgebra of algebra A, or subring of ring A, which is algebra over R. Then we can consider the following, which we call fiber ring. A tensor product over R by K of P. It's isomorphic to localization modular AP, and this will be fiber ring. Let me try to explain why this is called fiber ring. Just if we have in geometric situation, you have spec of A, spec of R, and you have morphism. Since you have an inclusion, you have morphism in this direction, and you have a subvariety which is defined as P equals to 0, just zeros of P. And then fiber over this spectrum, this subvariety should be a spectrum of this. And somehow you just okay. Let's give it the definition. We say that A is R. Let A be an R algebra. And we say that A is AN fibration. Over R. If A is finitely generated, and for each p which is prime divisor, prime ideal in R. This fiber ring is algebra in n variables, polynomial algebra in n variables over this field. So geometrically, this should be yes, A should be flat. I have not. Okay, let it be flat algebra. So it means that A is flat over R. Of course, you can eliminate this conditional flat, but then what we should say would be false, but okay, let it be flat. And the geometrically, if this and these are rings of regular functions on some varieties, it means that you have mapping from one to each other with fibers equals to affine spaces.
Fiber of every subvariety,
Subvariety,
every image
yes.
of every subvariety.
For every in every point, not only close, but
Please tell again, what is the geometric meaning of this definition?
that if you have two varieties, you have mapping one to each others, and you consider zeros of some prime divisors, a subvariety, irreducible subvariety, then its pre-image should be just product of this and affine space.
Take this prime divisors to be zero divisor. What should it mean?
Maybe prime ideals.
Prime ideals.
Prime ideal to be zero ideal.
If zero ideal is prime, then you have just irreducible. Okay. It should be. Let me think about this. But maybe I should say that R P is okay. Let A be so R be a domain. Then zero divisor is you can divide, I'm sorry, birational, you can divide on any field. Okay, let me say. Let us consider a particular case. Let R be domain. And A should be an R algebra. And P should be 0. Then you consider K of P. This is just quotient field. And then you say that A is tensor product with this quotient field. It means that you can divide on any element from R is to this quotient field algebra and variables. Yes. So it does not implies that A is polynomial ring in variables, but when you can divide by any element from R, you obtain algebra in n polynomials over quotient.
Algebraically it's clear, but what is the geometric meaning?
Geometric means
your picture is misleading.
Yes,
It's
yes,
something
yes,
that's
yes.
like the pre-image is a direct
I'm
product.
sorry. Seems that this picture is not so good. Okay. Let me erase the. I don't understand the geometric meaning.
Well,
Somehow it's
the fiber of the pre-image of closed points are affine.
Yes, the pre-image of closed points is isomorphic to affine space, but what can I say about pre-image of subvariety? I don't understand. Do you understand?
It's birationalized.
But still, at least it justifies the word vibration. Still justifies the word vibration. So if you consider any closed subvariety, over any point you get a affine space. So
No, not on any over any point, over generic point.
Yeah.
So,
Yeah, on any closed points, any point you
for
can.
yes.
Well, for the varieties, it means that if you have a point, then the pre-image of the point is isomorphic to the affine space.
But there are some extra conditions on pre-images of any reducible subvariety. And this condition we don't understand.
No, it's about pre-images of generic points of the varieties. It's more scheme language. So it's kind of difficult.
May I give a guess that over, if we take 0, means that over there is some open subset with trivialization. So over the whole base there is trivialization chart, and for any closed subset there is again.
What do you mean by trivialization? So there exists an open subset in the base, such that the pre-image is a direct product with what? With affine spaces,
yes.
or with some birational...
No, with the affine space. So for the space is the affine space. And for any closed subset, we have this open subset open in it, so open closed one, where we have that.
Okay, let me try to proceed because, yes, I'm not so good in this field and I can't say correctly that what this means geometrically. But let me state somehow a problem and then we can try to explain what it means in some particular case. Okay. Problem which is called AN fibration problem, which was stated by Weisfeller and Olgachev in 1974. Then if R is some good ring, regular noetherian of dimension D, A is AN fibration. Is it true that A is isomorphic to symmetric algebra over some projective model? If R is isomorphic to just polynomial ring, then every projective model is free. So is it true that A is isomorphic to polynomial ring over n in some n variables? So let us start with just this statement. And then let me say what is known. If for any d, if n equals to 1, the answer is yes. It was proven by Kobayashi and Mainichi. In 78 and in 85.
I think it's Kaufmannish.
I think yes. And for d equals to 1 and n equals to 2, there is a theorem due to satire proved in 83, and the answer is also yes. And in all the other cases, the problem is open. Maybe I should say something about epimorphism problem, which I have raised. So there is a theorem due to Abhyankar, Moch, and Suzuki, which said that if you have two variables, then let me return to epimorphic problems. If you have C of x, y, modulo f, and this is isomorphic to one variables, then f is coordinate. In bigger dimension, it's not known. Okay, and now we should consider a very particular polynomial. This example due to Bhatwadekar and Dutta. So this example in 1994, they consider the following: let A be a polynomial in 4 variables, x, y, z, w. And we consider subring R, which is polynomials in 2 variables, w and f, where f is rather huge polynomial of this form: x plus x squared zw plus y w squared plus x y squared w. And for this polynomial, the following theorem is true. This theorem have lots of conditions, lots of items, 7. Let me start with this one. If we consider R, some extension of R by W in power -1, then F became a coordinate. So it equals to R, C W1 divided by W, F, and how much? 2 more coordinates. The second condition, that this inclusion R to A is A2 fibration.
These three in the previous item, they are algebraically independent, yes, or demonstrated? Or it is follows.
For algebraically independent.
W1 divided by W.
W and 1 divided by W cannot be algebraically independent. They are dependent.
This depended by F, of course, independent, because it's not a polynomial in W, and 1 divided by W. So, of course, these two algebraically independent. The third one is when you add some extra polynomial, extra variable, then F became polynomial ring over R. Not A, but this extended algebra. Therefore, means that A modulo F is a polynomial algebra in 3 variables. 5 is very similar, that A divided by modulo F plus F of W, some polynomial in 1 variable. Also, polynomial in 3 variables. The 6 is that when you consider invertible to F, then it became also okay, the 7th one is, let it be 6.
It's in the case F is any. F is any in number 5, yes?
In number 5, F is any polynomial in 1 variable. And the question, somehow problem, is whether F is a coordinate in A, and this is, let it be 2 questions, A and B. B question is whether A is isomorphic to R, a polynomial in 2 variables over R. So this means that not only that F is coordinate in A, but F and W can be considered in one system of coordinates. And both of these questions are open. So let us...
But if this is not the case, then we will have counterexamples to this.
Yes, if what does it mean that this is open? Then some people try to check that F is a coordinate, apply some different automorphism, but nobody succeed. So if F is not a coordinate, then you have counterexample to epimorphism problem, because this factor algebra is polynomial ring, but F is not a coordinate. And if part B is not true, then you have counterexample to A2 fibration problem, because this is A2 fibration, but this is not polynomial. This is A2 fibration over a polynomial ring, but this is not a polynomial ring over this subring. So this is a candidate for being counterexample to these 2 big problems. Okay, and what should I say? That, to be honest, it's a rather complicated problem. If I, of course, if you see on this big polynomial, it's not very similar to a coordinate. But if I apply a rather complicated automorphism, then it have very complicated coordinates. So it's an open problem how to say, considering this polynomial, whether it's a coordinate or not. Let us maybe start to prove this theorem. My goal to this talk is as follows. Firstly, I would like to just prove maybe three. I would like to go to the fourth one. Three, I will not prove three, but we discussed 1, 2, and 4. And this is this should be proof which is written in Neena's paper, and this is based on flatness and somehow on commutative algebra. But when I see this one, I think that this is just a hypersurface. This hypersurface is isomorphic to affine space. It seems that it can be a proof this isomorphism without any difficult theorems, without any technique, just using our technique about local and important derivations and so on. And I would like to present you some technique based on local and important derivations, which prove that this quotient algebra is a polynomial algebra in three branches.
Did you find three commutative entities?
I find one. Yes, but it is confusing.
Okay, but just to understand. So this paper is more than 30 years old, right?
Yes.
You was interested in this because of what? Because you find a new proof? Or because you want to or answer this open questions?
Yes, I can somehow answer. First of all, I think that we should have some list of these counterexamples because of these possible counterexamples. I don't know whether they candidates. Just to think about these problems and some connected problems. And second reason for me was the following. It is rather useful for me to have some non-trivial realization of affine space. I was thinking about cancellation problem. Cancellation problem, let me just 2 minutes say about cancellation problem. If you have an algebra A, let that be B, and you take extra variable, and it became a polynomial ring. Whether this is true that B is isomorphic to polynomial ring in n-1 parameters. And there is a technique which is used to generalized cancellation problem. This means that if I take B and C, I would like to prove that polynomial ring over B and C are isomorphic. And this technique is as follows. You consider some quotient realization of this B. Just give by some equations. And you can modify in some these equations. In some way, you can modify these equations. And so to apply this for affine space, for free algebra, you should consider this algebra as a quotient realization with non-trivial equations. Of course, you can realize this algebra as just algebra with empty set of equations or equation just one coordinate equals to 0, but this set of equations cannot be modified by this technique. So my hope was that if I can realize this algebra some non-trivial way, for example, in this case, then I can modify this equation and obtain a counterexample to Zariski Cancellation Problem.
So I don't understand. So assume that you realize this algebra as a factor algebra. Okay.
So let's C3 is isomorphic to C of X, Y, Z, W modulo F. Then you modify F in somehow and say that when you add some extra variables, it's equivalent to C of X, Y, Z, W divided by F bar of S. And if after this modification this is not polynomial ring, then you win. The problem is that you can't modify empty set of equations, but now I can't modify this equation also. Of course, I have not counterexample to Zariski Cancellation Problem, but that was my hope, and still I think that it's rather interesting to obtain realization of free algebra as quotient ring in some non-trivial way.
Okay, but this was your non-realized aim, and the subject of your talk is a new
The subject
proof,
of my
it's a
talk
new
is
proof of this theorem.
no of this point of this theorem.
And in the original paper, LNDs were not used.
For this point, not. Let me just give a sketch of original proof, and then we discuss.
I am confused. If this is true, then how can you get a counterexample to Zariski Cancellation Problem? Because if you apply
No, you have first step to have to obtain a counterexample, but the second step is non-realizable, so you have not counterexample to. This is true, and we are still have not counterexample.
Sorry, I want to clarify. The interesting form of the fibration problem is that if we have an affine space fibration over an affine space, this is again an affine space.
Yes. I think that this is not only an interesting case, but for us, yes, this case. Okay, I have no ideas how to prove that f is not a variable. So let us discuss just this. For the first one, you just can consider some original proof. The first item can be just be done very explicitly. You just put down some explicit polynomials. This G is, let us start with P. P is xz plus y squared. G is equal to wy plus p. H is somehow more complicated. W squared z minus 2w yp minus xp squared. can be checked that A of 1 divided by W is isomorphic, is equal to C of W 1 divided by W F G R. It's just an exercise for everybody. Just rather explicit.
You should just express y, x, y, z, and w.
Yes, yes, yes. If you would like to, I can explain how to do this, but this is just explicit multiplication. The second one. The second one is just some crucial thing about A2 fibrations. It seems that it can be proved that A is R modular is a flat R modular. Using two rather standard theorem which is written in any book on commutative algebra. The first one is that if you have a ring R and you have polynomial ring divided over F, then this ring is a flat R modular if and only if this polynomial is primitive. This means that let R be UFD, and primitive means that the coefficients of this from R are coprime. And the second is about some sequences.
Sorry, coprime together.
Coprime together, yes. They generate trivial ideals. And the second, in some conditions, say that if some algebra is flat over small algebra A, then it can be proved that C is flat over B. There are some conditions. They are not very complicated, but here the scheme is as follows. You consider as this smaller algebra, let it be C, and this is A, and this R. You consider for this smaller algebra just C of W. You apply this theorem to obtain that this algebra A is flat over this, and then apply the second theorem about flatness over R in some sketch, and you should deal with these conditions, rather technical conditions, if you want to prove this. Okay, let us believe that A is a flat R model. Then you consider a prime ideal in this ring R, which is C of WF. And there are two cases. The first case is that W belongs to this P, and the second case if W don't belongs to this P. If W don't belongs to this P, then it's invertible, W invertible modulo P. And then you apply, you have just 1 divided by W, and you apply the first case and prove that when you localize by this P, then when you multiply A to this K of P over R, it should be just polynomial two variables, because it's just localization of this algebra, which is polynomial ring. And if W belongs to P, then you can say the following. You just can consider this C of X, Y, Z, W times C of F, W modulo P W. And when you have this W here as coefficient in, let it be C of W of X, Y, Z. You can move it to this one, and here P contains W, and this is just 0. So you can eliminate W and consider, so this is isomorphic to C of F, this is X, Y, Z times C of FW modulo P. And modulo W, when you consider this F, all of this is divisible by W, so modulo W, F equals to X. So you can replace this F to X, and then all is proven because you have extra two coordinates Y and Z, and you obtain that this is polynomial in two variables. So this is just idea how to prove that this is A2 fibration.
So in this case, in the lower one, we will have that A is we may assume that we already localized by W, and it's just
and you obtain this one,
and
you
the polynomial of two rings over R, and
these two variables
yeah,
are
we
X
have
and
that
X.
A is a polynomial of two variables over
Yes,
R.
variables G and H.
Yeah, and so and locally it is obvious that H
Yes. Okay, and what about how to use this 4.4? Let me discuss original proof of this 0.4. Just you say that let us consider S is C of W. And you consider this ring B, should it be B? This B is A modulo F, and from point 2 follows that B is A2 fibration over S, which is, let me remind that C of W. And just you eliminate this F, and so it should be A2 fibration over this S. And in this case, you have answer for A2 fibration problem due to Satire theorem. And you apply this theorem and say that this, if you have A2 fibration over polynomial ring in one variable, then this ring is also a polynomial ring. So it follows from this Satire theorem. And okay, it's a rather beautiful application of non-trivial theorem from commutative algebra, but for me unclear if I have this isomorphism, I should construct some explicit variables such that this is polynomial ring in 3 variables. And let me finish with original proof in this step and try to explain how one can obtain this explicit isomorphism. If I know that something is polynomial ring in 3 variables, what should I do? Polynomial ring in 3 variables have lots of LNDs. And some of them are LNDs with slices. Okay, let us consider this ring B, this quotient ring. And let us try to obtain at least one LND. How to obtain LND on vector algebra. So let me just rewrite. You have C of x, y, z, w, and you have modular f, where f is this one. X plus x squared zw plus yw squared plus xy squared w. I don't know. It's an open question whether there are LNDs which which cannot be obtained by the following construction. But the standard construction is as follows: you consider an LND on these algebra variables, polynomial ring in 4 variables, such that f in the kernel, and then this local unimportant derivation can be considered as local unimportant derivation in this vector algebra. Okay, let us try. We consider derivation such that d over x is 0, d over w is also 0, and we try to put d of z and d of y in such a way so that this should be 0. Z we have only here, and y we have here and here. So it should be the following. Let me just take d of y equals to minus x squared, and d of z equals to w plus 2xy. Just this x squared, this is df dz, and this is df dy. But divided by w, and here is minus. And since this is true, then d of f equals to 0. And you obtain a local unimportant derivation on this quotient algebra. Okay, you obtain local important derivation, but in polynomial algebra in 3 variables, you should consider maybe local important derivation with a slice, because it's the simplest case. But this locally important derivation, to be honest, I failed to consider some other locally important derivations. But here you should say that this is not with the slice, because all the images are in the ideal generated by x, y, z, w. But nevertheless, now we will show that this is just not a reducible local important derivation. This is a replica of a local important derivation with a slice. Okay, we just say that here all of these is just w multiplied by g, where g is the same as in point 1. G, one can say that this is x squared z plus wy plus xy squared. So, yes, this is a domain because of this is proven, and this is a simple proof, and we can use this, and this follows this. This is a domain. Okay, let us just rewrite this. F equals to x plus wg, and if we consider x, it should be f minus wg. So in this is in polynomial algebra, but in quotient algebra in B, let us say that in B this is 0, and x equals to minus wg. And then we can rewrite this all just as follows. This is equals to minus w squared g squared, and this is w minus 2wg1. And then you can see that all the images is divisible by w, and since w is in the kernel of our locally important derivation, I didn't explain why this is locally important derivation, but this is just a triangle one, and it's trivial that this is locally important. Then you consider derivation delta equals to d divided by w. So delta of w equals to 0, delta of x equals to 0, delta of 1 equals to minus wg squared, and delta of z equals to 1 minus 2g1. Okay, now it's at least seems to be irreducible, because 1 is in the ideal generated by this and this. And hence we can try to prove, what should we prove? We should prove that this L and D have a slice. So we should find an element S such that d delta of S equals to 1. And we should explain that kernel of this locally important derivation is a polynomial ring in 2 variables. If we prove this, then we say that our algebra B is just polynomial ring of three variables, because when you have an LND with a slice, then you have polynomial ring over the kernel in one variable. So let me erase all of this.
I'm sorry, and why kernel is a polynomial algebra?
This what we should prove. So the idea is that we step by step try to find this S. And in these steps we find generators of the kernel post. But it's a little bit many computations. Okay, let us say that G, it is not an irreducible element also. Let us consider G is written here. I'm sorry, this is equals to W multiplied by G, and this is just G. G is equals to X square Z plus WY plus XY squared. Okay, and since X, where it is, X is equals minus WG, we can substitute it here and obtain that it is equal to W multiplied by WG squared Z plus Y minus G Y squared. So G is divisible by W. Okay, let us denote all of this by alpha and ask yourself what is delta of G, since delta of X is equals to 0 and G is a factor of X and alpha is factor of G, so all of them are in the kernel. So you have the following. You have these two guys, and delta of Y equals to minus, where it is, minus W cubed alpha squared. I just replace G by W alpha. And delta of Z is 1 minus 2WY alpha. Okay, we have this one and we have this one. We would like to obtain a polynomial just in W as an image of our local unipotent derivation using, applied to an element. It can be, let me say that, let us consider the following. Here we have G is equals to WY, yes, W alpha, I'm sorry. And here G is equals to W alpha. And we can use all this guy, that this equals to this, to obtain a formula to WY. Let us try. WY equals to W alpha multiplied by 1 minus w squared z g plus w y squared. So y is divisible by alpha.
So now we are constructing S.
We are constructed S, but by some steps. This is first step. We would like to obtain w in some power, a polynomial w in image. So you can just say that let us erase this w since we have a domain, and then y equals to alpha multiplied by this guy. I'm sorry for big amount of computations. And hence there is an element, this one, which is y divided by alpha. Let us try to understand what is delta of this guy. Since delta of y is minus w cubed alpha squared, then this is minus w cubed alpha. And if you can see here, you have alpha, w. To obtain w cubed, you should multiply it by w squared. And to obtain y, you should consider delta of y squared. So y squared, yes. Delta of y squared divided by alpha is equals to minus 2y w cubed alpha. And considering this and this, we obtain that delta of w squared z minus y squared divided by alpha is equal to y squared. Sorry, this is the...
So y squared or w squared?
Here what w squared. So I multiply this by w squared. W squared minus 2w cubed y alpha. And here also 2y w cubed alpha. This and this I just contract, and the remaining part is w squared. So we obtain this guy. This is not a slice, but this is the first step toward obtaining the slice. We obtain power of w as an image of our ordinary important derivation. And then we will try to improve this to obtain a slice. Okay, let it be beta. And then we try to follow this. We can substitute all the guys which we have in beta. So beta equals to w square z minus y divided by alpha. This is this guy. And multiplied by this is y divided by alpha. I should square it and multiply by alpha to obtain y squared divided by alpha. What is the idea? The idea that I would like to divide this by w. Because here delta of this guy is w squared. I would like to obtain a polynomial such that delta of this polynomial is W and then divide it by W once again and obtain a slice. But this is not divisible by W. All this stuff is divisible by W, but there is one term such that this is not divisible by W. Then you can just firstly add something from the kernel to this guy. Then the image, since you add something from the kernel, the image will be the same. And then it would be divisible by W. So here, if you consider beta plus alpha, then it is divisible by W, and you can consider this guy divisible by W, it should be gamma. And then by the same technique, then you can say that delta of gamma equals to W. And by the same technique, you can add something from the kernel such that this sum will be divisible by W and divide. And then you obtain that S is gamma plus 2 alpha cubed divided by W. And this is the slice.
But can you write it down with original coordinates?
It's rather huge because you should just substitute one to each other. So you have, let me write down, you have beta, then you apply this alpha, where my alpha, this alpha is guy. And then you apply this one.
Alpha cube. Okay. Alpha cube will be rather terrible.
Yes, this is, yes, it can be computed, just substituting, but of course it's rather huge. And then you have delta of S equals to 1, and you have generators of kernels. You have these two. Delta of alpha equals to 0. Let me write it here. Delta of alpha equals to 0, and delta of W equals to 0 also. And it is not a complicated deal, but you should go from the end to the beginning. And I have not proved that these are generators of the kernel. But you can just go in the opposite direction and just prove that X, Y, Z, all of them in B belongs to C of S alpha W. Oh, W of course belongs. So you just can obtain explicit formulas for X, Y, Z in variables S, alpha, and W.
I don't understand.
Well, just here, for example, you have S, you have alpha, and you can say that gamma equals to SW minus 2 alpha cubed. This is just from this.
These four variables are algebraically independent.
No. It's in B. They are dependent because f equals to 0.
No, modular relation.
Modular relations, yes. All these explicit formulas are modular relations. So it's in fact algebra in B. And you can just obtain formulas for all these generators as polynomials in S alpha W in B. And since this is a slice and this are from the kernel, this proves that these are generators of the kernel, and so this B is just polynomial ring in 3 variables. So, in this way, we construct just very explicit generators for this algebra B. So this is C of X, Y, Z, W modulo. Okay, I have tried to obtain something about proving that F is not a coordinate using these explicit generators for the factor algebra. But I failed, and now I have no ideas how to prove that F is not a coordinate using these explicit generators, but maybe it's interesting that we have these generators. And we have very trivial, just straightforward proof that this B is a polynomial ring in 3 variables. I'm sorry, I understand that this is not very enjoyable to follow these computations, but okay. I think I finished.
Okay, thank you. So, any more questions, comments? Today we have a big number of participants. Okay, so just summarizing. The result is that some quotient of the algebra polynomial in 4 variables by 1 relation is an algebra polynomial in 3 variables. And you apply the technique of local important derivation to deduce this.
And maybe the interesting part of this result is that I have explicit generators of this polynomial algebra in 3 variables.
And what is the way, how can we theoretically prove that this is a variable? What is possible approach?
The possible approach is just to include it in. So, what is my hope to prove that this is not a variable? Because if these are generators for the factor algebra, then the initial variables, if they should be f, w, alpha plus f multiplied by something, s plus f multiplied by something. This is if if this is a polynomial ring of over f and w. If just we want to prove that f is not a variable, then you should f multiplied by something add to w also. So this should be C of x, y, z, w. But I have no ideas how to prove that this is not the case, that you have not variables of this special form.
If you will represent x, y, z through 4 expressions of this form, you will prove that it is a variable.
Yes, yeah, if you, yes, of course. But what should I mention that if you try to consider w alpha s, this is not a set of variables, so this is not equals to c of x, y, z, w. No, just you compute Jacobian, and this is not a constant. But so if there is a set of coordinates of such a form, then it's non-trivial, and you apply this huge f multiplied by something to these 3 guys, and this is very huge. No, this is, of course, should be true because it's an open question whether f is a coordinate if it can be included in some simple set of generators, then somebody have proved this. But to use this form for proving that there is no such, I tried to use this form for finding generators in this coordinate system, but I failed.
But this is a very, perhaps a naive approach, just to find four generators. But maybe some more advanced approaches are possible.
So
your lovely LNDs, maybe to apply them to prove that D is a variable.
I don't know how. In my opinion, we should think about this approach using commutative algebra, which I try to present as an original proof, because it's a new technique for us, and maybe some general technique using LNDs and this can be used for this. But now I have no ideas how to proceed, in what direction to proceed.
Okay, no more questions, ideas, propositions? If not, then thank you. So now